introduction.
Yes, we can see yours.
So I'm an example of, I guess, a computer scientist and machine learning by training person. I got my PhD from computer science department at CMU. And then I actually went ahead and got a job at medical school so that I would directly sit next to the clinicians to understand the problems and really start to tackle them at the core of, the clinical aspect of the problem. And, I'll share some of our experiences here. Hopefully it will be useful for you guys. This work is towards tackling, the issue of dementia early detection in the real world setting. And I'm going to talk about using electronic health records and also MRIs to facilitate this task, to work towards this task. So we all know Alzheimer's disease continues to be a killer, one of the top killers, and there is nothing useful for it. Last year, there was this Adalimumab that was FDA approved. It created so many controversies, so many people from FDA quit because the data wasn't there. And so the conditions, the situation in terms of treatments available, clinical trials for Alzheimer's disease is a mess. And so early detection has now become the key aspect of a hope for a treatment. So at the moment, all NIH clinical trials are addressing mild to moderate AD. They don't even bother with advanced AD anymore, because if you want to do something, you should start before there's too much cell death, basically, and too much atrophy. And that brings us to early detection for AD. And then there are actually a couple of larger scale randomized clinical trials, which are the gold standard of evidence in medicine. One of them was actually like 2 years ago, I think, completed. It's called Sprint Mind. It's very large scale, and their focus was actually cardiovascular improvement of elderly. But then as a secondary outcome, they actually measured conversion to mild cognitive impairment and AD, and actually they saw as a statistical significant effect of intensive hypertension control in preventing conversion to MCI and AD. There was still conversion, but the rate has been reduced. Okay, so that is something that is potentially preventative if we know risk of Alzheimer's disease or MCI. So that's something we can possibly do at the moment, forgetting about Adalimumab, which is a lot of controversial, aspects at the moment, also including like who's going to pay for it, is insurance going to cover it, etc. There's another trial which is addressing controlling basically vascular issues. This one, cholesterol, and using statins, etc., to see whether or not they make a difference. So these are all kind of new evidence that is coming up. Okay, there is something we can do. Like, let's just completely not give up on these disease and these elderly to get that. And of course, there's also a lot of more like planning use cases for early detection, and also better enrollment in clinical trials. If we can enroll patients who are just about to transition, then the statistical power of that trial is actually going to get higher. So we can actually cycle through different hypotheses faster. So this is kind of the state why early detection mattered. And then, unfortunately, this is like situation where, okay, we need early detection, but then clinical trials are all based on research cohorts, and research cohorts are actually pretty much exactly not representative of people who actually get typically, they're at high risk for dementia. So first of all, people with lower education, people from racial minorities, they're actually more or less excluded from these enrollments in this cohort. And then there's so many disparities in terms of access to even neurologists to even get the diagnosis or get early diagnosis. A lot of these patients at the moment, 2/3 of AD patients are women. Risk factors are correlating with race and socioeconomic factor. Here's a New England Journal of Medicine showing you some basic risk factors for dementia, which have been all supported with multiple studies, etc. Early life, low education, midlife, like vascular issues and like metabolistic issues, and then towards the end, depression, social isolation, physical inactivity. All these things kind of like lead towards increased risk. And if you look at these risk factors, they actually correlate with race. And they're like, if we now look at certain cohorts, for example, acne, or for example, NAC, if you look at these, look at the distribution of the patients. Okay, we are talking about majority white population who signs up for these studies, and actually, I didn't put it here, but like the education of these patients is like, they're all like college educated. So it's a totally different cohort than people who are actually high risk. So this is a problem. It's a really big problem. And now, okay, I sit at medical school, I talk with these people, and then the majority of dementia screening and diagnosis is actually not happening in any neurologist center. It's actually happening in primary care offices. But even then, those primary care providers are busy. They are, it's an elderly patient. They have so many other conditions to deal with, like they have cardiovascular issues, they have diabetes, probably, a lot of different things that we get diseases. And so they actually neither have time nor have education to actually apply these screening methods. That's another problem. And of course, as you can imagine, the more high-risk patient is for dementia, they go into this cohort, which are actually more neglected in terms of a lot of their care, including, cognitive screening. So maybe that is why we don't have a treatment yet. Like the direction of what needs to happen, the direction of what's happening are like really different directions. And that's been very frustrating, but also it tells us potentially an opportunity to improve something. And so now I'll tell you more, as we see, but I'm at the medical school, a very large medical school with it's New York City. It's very diverse racially, one of the most diverse cities, on earth. And also it's very large, it has a lot of people. And NYU has been around for quite a few years, so the data that we have is somewhat continuous. So it's quite interesting data that we can use to actually kind of move beyond just research cohorts and actually get closer to reality of who's getting these diseases, what kind of data they have, and whether or not we can do early detection where it matters, with clinical data. So I'm going to talk briefly about two aspects. I'm going to kind of like talk very quickly because I only have half an hour. However, I'll mention this to you and then let me know if you have questions afterwards, or send me an email. One aspect I'm going to talk about is using electronic health records for dementia early identification and primarily risk modeling. And then the other aspect is using structural MRI, T1 MRIs, which are somewhat cheaper to measure and easier to measure, to see whether or not these modalities can actually help us to some extent with early identification. And I completely resonate with previous speaker that, look, there's so many studies out there which are just, they got lucky in terms of like they tried so many different iterations, and yeah, okay, one of them is going to give you good results. So my team's focus is actually really external validation, like moving beyond this like results that we get by chance. So like this study, I'm going to talk about a work we did training some model, a deep learning model on ADNI, which is one major famous data set. There's like millions of studies on that. However, our approach is different because we actually evaluate our model on an entirely different large cohort called NAC. These are both two major cohorts for Alzheimer's disease. That's completely our external validation, and we got some promising results. And I will also mention a little bit about evaluating it now on NYU Alzheimer's Center's clinical MRI data. Okay, so a lot to talk about. But for those of you who don't know what is EHR data, so electronic health record systems are these IT systems that hospitals have started to adopt primarily after the economic collapse of 2008, if you remember. They needed to save money. Obama gave them a lot of incentive to switch to electronics so that actually like operations would be more seamless, they would save money, etc., more transparency. And as a result of that, a lot of hospitals one by one started to switch to some electronic, basically IT system. But the good thing is, well, good or bad thing, is that they all, at the time, there was only one company that offered pretty comprehensive EHR system. So most hospitals switched to that one, and that company is called Epic. So at least there's some uniformity in terms of like these systems that different hospitals adapted. So once they all switched to this IT system called electronic health records, like it captures records of patients. So suddenly everything that happens gets captured digitally, and that actually means data. It's a lot of data. So since 2013, which is when NYU's finished their switch to this one particular Epic system, NYU has serviced 7.5 million patients with different types of services, so modality of diseases, etc. As I told you, NYU is a relatively wide footprint, but it's within New York City area, but a little bit broader. And then if you look at, okay, what kind of diseases are we talking about? We're talking about hundreds of thousands of patients across different disease categories. And usually their care is somewhat continuous. So we kind of have their data 5 years ago, we have their data now. And if we wait 2 more years, okay, we also have 2 more years of data. So we suddenly have like 8, 9 continuous years of data for one, one individual. And then you can start to look at different patients. And that gives you an interesting power to do predictive modeling, because if you have time, you can build outcome from like future and then use past as features, etc. There's a lot of interesting things that can be done. So in terms of dementia, that's one of our projects. It's one of the things that my lab is super interested in. We started with a retrospective design. Retrospective means, okay, we pull out a data set, we build our input and output, start building some models, and we kind of assess, like kind of in vitro, computationally, we assess how good our model has been. And that's only one stage of like really clinical deployment and clinical validation, but this is the first stage, and I will tell you about it. So as I told you, EHR data has time in it. So you see my arrow, right? So typically you kind of have, let's say, you start to say, okay, from 2018, before 2018, I'm going to use that data as my variables. And after 2018, let's say I'm interested in whether or not somebody is at risk for dementia in 2 years. So between 2018 and 2020, I'm going to use that data to see whether or not they actually got, a new onset of MCI or dementia. And then I use these variables, which come from like before 2018, to do prediction. And of course, now the question becomes, okay, how do we handle these variables? How do we build them? How do we also build this model that predicts from these variables to the outcome? And then, so NYU Langone, I told you, it's a very large cohort, as I said, like 7 million patients across different times that have visited NYU. If we clean up our data with continuous data, patient over the age of 65, we still had 840,000 patients who would be included. Of those, 40,000 had a diagnosis of MCI or dementia. About 57% of them were female, of the entire cohort, bigger cohort, not this sub-cohort. Entire cohort, 57% is female. It's relatively racially diverse, much better, in terms of like, let's even look at just one metric, which is how much of our cohort is just white, compared to NAC and ADNI, which are all like 83 or 92% white. You're talking about like 57% white. So it's much more diverse in terms of racial aspects. So it is very promising. It's more real, in terms of closer to reality. Now the challenge, and maybe I'll mention a little bit technical aspect of it, is how do we go from these EHR variables? What are variables we're talking about? Those inputs that I'm talking about, okay, what are they? What's the dimensionality? And how do we build a model that predicts a single outcome, let's say binary outcome, whether or not there's an MCI or AD? So electronic health records are, if you think about them, if you want to think about them, but every time we go to a doctor, whatever diseases, labs, etc., we have it recorded, and that's kind of EHR. It's almost like a lot of CSV files. It's a lot of tables, which with timestamps, and then like a lot of binary indicators, sometimes continuous values, etc. So diseases that are diagnosed in different time points are usually documented as ICD codes. People call them billing codes, etc. There are over like 69,000 ICD-10 codes, or 14,000 ICD-9 codes, and this number actually keeps increasing because new codes get introduced. Then all the lab values that could possibly be ordered, there's like over 70,000 different lab orders, glucose, cholesterol, etc. There's 70,000 of them at the moment, but then it also increases. Then there's 90,000 potential medications at different levels. We can start to look at them, and then different procedures like surgery, etc. There are also like at some level there's 40,000 of those. So overall, primarily what we work with typically in my lab, and it's not even including a lot of other variables, but we're talking about almost 500,000 variables that are encompassing, somebody's state of health at certain time point. Okay, so And then, okay, that's one challenge. And then these variables are actually correlated. If somebody has diabetes, they're most likely that their lab value is probably a little bit off in terms of, let's say, A1C and glucose, which are the metrics for diabetes. They're probably a little bit obese, but we don't know, but the probability is a little bit higher, right? There are certain conditions that the probability goes up. So there are correlations between all these 500,000 variables. And it's such a complex setting. So there's a lot of ontologies these days, but there's no mapping between different groups of variables. Actually, at the moment, there is nothing that maps, let's say, low encode to diseases. And manually, okay, mapping 70,000 with another 80,000 variables is just not possible, and keeping up with that is also not possible. So we need better actual methods to actually leverage and learn the relationships between these variables so that we can actually build certain models. And by the way, yes, we also can build linear models, and we have done that as well. That's typically our baseline, and typically a little bit more leveraging relationships between them, because we have so much data. Typically, it leads to better results. So our job is to actually learn these relationships between all these 500,000 variables and then use them to predict. So one of our papers, which actually I refer you to read it potentially, because there's not enough time to go over that, but it uses graph neural networks, okay, for electronic health records. And this came after almost 5 years of us building different levels of models. So it's not like, out of nowhere. The first few years, we were working primarily with linear models just to see, what is going on in our data. And then slowly, okay, we kind of have a good idea of what is a linear model getting us. And we started basically scale-learn models, random forest, etc. And then we moved on to neural networks to see whether they add value. And, in this paper, we actually do compare to all those other models. And just briefly, I guess, for you guys, in terms of what is graph neural network, and in this case, it's a graph attention network version of graph neural network. It's like each disease that the person has. Each disease could be a node, and I told you, we want to learn this relationship between the variables. So each disease iteratively starts to look and see from among other variables that the patient has, which ones are related to it, and whether or not, during the modeling, can we leverage those other variables to improve the representation that we have of the patient. So just briefly, I guess each patient comes with a bunch of observations. Like they have, let's say, I stick with this example, diabetes, they had some lab value that they measured, etc. And then they become a map to some kind of a latent space variables, and then we start to learn relationships between them. And then, the actual term is a multi-hit attention, which we learn per node, and we iteratively improve the representation power of our model. Sorry if it's too much, skipping over the details. I'll be happy to answer this during your question. And then eventually we actually build a classifier on top of the last layer of our graph representations. And that classifier will be trained against the outcome, yes or no, that will have MCI or dementia. MCI is mild cognitive impairment. Mild cognitive impairment or Alzheimer's disease in the next 2 years. And we typically train them in a way that, okay, if somebody already has that, we exclude them from the population. So we only care about new onset MCI or AD, so that we can actually train the model to do early detection, not classification. And this particular paper has a neat new addition, which is called variational regularization. I'm actually going to skip over that, but it improves the representation power of our approach by introducing variational approach. So, so that's kind of the graph neural network. And then now, at the moment, the state of the art in Alzheimer's risk modeling from EHR is a logistic regression model from, I think, 30-something variables, which is pretty simple. These are the variables, these are the coefficients, basically. So we could actually replicate this model. It's called eRADAR. It is trained over a research cohort, actually, which is 92% white. So it's a little bit like, it's from the things that I kind of get a little bit suspicious when I see this kind of, data set in terms of their applicability. Anyway, this is our baseline model. It's pretty, it's been published before recently, so we can compare it. And then if we compare it with our with a very extensive definition and very proper, extensive inclusion criteria setting. We kind of have multiple aspects that we will include in terms of definition of MCI and AD. We exclude anybody who has any of the notion that they are already in the system, they're already monitored. If we do that, and if we look at the new heldout test set, completely set aside, we're talking about 79,000 patients, of which 2,500 get new onset MCI AD in 2 years. And then we actually have the model that we had trained before, and also the eRADAR model. And then if we start to look at their comparison, we see that, eRADAR model actually is lower, maybe not surprisingly, but also eRADAR model is actually consistent with what they have reported. So our data seems to kind of, match and our results. And then our, a little bit more complex model turns out to be better. That's one aspect. The other aspect is there's a little bit more drop in terms of difference of race, like green is white and then red is non-white. And these lower curves are the eRADAR model, the statistical model, which is already actually the topic of funding for 2 large-scale NIH trials. So like this model is already considered advanced enough for NIH to fund $5 million to enroll that. And so this one, there is a significant drop in terms of performance for non-white population, whereas in our model, partly because our data is our cohort is diverse, partly because our data is our model is a little bit more comprehensive. That drop, we don't observe that. And also, if you look at patients who actually had MiniCog or MoCA or MMSE screening in that data, the performance differences also exist. So that's very promising in terms of, so that the EHR data and using the model, which is a little bit more powerful, actually does, see, at least on retrospective analysis, on the data that we have pulled, it seems to be giving us good and promising results. Now, I am interested in actually going and really tackling this. So our next level is asking this question: does it actually make a difference? Does it improve the actual problem that we want to solve, which is, does it make a difference in real clinical setting? And now is when the next stage of the problem, begins. And this is a grant that we have, which have scored promisingly. So hopefully it gets funded. It's an NIH grant, which is about using an embedded pragmatic clinical trials. We have 2 centers in Brooklyn that are going to be part of the study, and then we randomize providers. Some of the providers will see alerts about a patient being high risk, and then they will be having any option. That's no forcing anything. You just have an option to whether or not screen that patient. And if the patient has cardiovascular problems that they're not dealing with, we are kind of suggesting, hey, their blood pressure is it's not managed. Do you want to manage that or not? Like, it's completely up to the doctor. However, we kind of bring it to the top of the agenda to some extent. And so that's kind of really exciting. And if it turns out that the results make a difference, that would be really great. And so that's kind of where we are with electronic health records. It's very exciting. And now I will very briefly mention just a few slides, I guess, using also structural MRIs towards the same goal. Also, MRIs and EHR are primarily different modalities. So at the moment, as we may have heard, so like PET imaging is the gold standard for identifying AD, but there's a whole lot of problems. It's not covered by insurance. It's expensive. It's invasive because of the injection of the tracers, especially for elderly, frail people. And then there's also non-standard, lack of standardization in terms of actually which proteins and tracers do we want to inject into the patients. But then the next question is, okay, if we are talking about atrophy in the brain shrinking, etc., can we also look at structural MRI, which is basically just looking at anatomy? And we saw in the previous talk that there's a lot of interesting, finding, comparing that with fMRI data. But my approach is focusing on large data sets and seeing if we increase the data sets, and if we focus on more and more complex models, but also really deep validation, do we see anything? Because there seems to be some signal, but like so many studies have so many different results, so it's kind of the space is a little bit confusing. So the focus is, can we use deep learning? And also we compared with a lot of other models to better identify AD or MCI, and then I guess the core of it at the end is, do these research-based models extend to clinical MRI, which we have at NYU, for example. So the data sets that we use, I kind of mentioned, ADNI is like bread and butter of neuroimaging, I guess, analysis. There's so many studies on ADNI only, which is very valuable, but it's a small one data set. And then what we are looking at is there's actually another publicly available data set comes from National Alzheimer's Coordination Center, NAC. It's more individuals, in fact, and it has more diversity in terms of types of dementia. And we also have, 2,000 scans from that one. So we use this data set completely as our external validation, and this data set is for developing the model. And this work is published now in 2 papers at the moment. You're welcome to have a look in terms of the details. The first paper, we kind of played with the data, and then with the architecture of the model only on ADNI. And then the second work is actually, okay, we kind of have a model, and then we kind of want to see how it actually works on external large data sets. And there are some aspects that actually make a difference in terms of designing architectures for medical tasks, which I'm listing here: instance normalization, less early spatial downsampling, and widening the layers. These were like our ablation-based study, and it kind of reminds us that, look, medical data sometimes has different properties than images of cats and dogs. So like maybe the architectures that are optimized for those settings shouldn't be like the only thing that we use. Maybe we should actually intelligently design architectures for specific tasks. And these properties I mentioned to you seems to be consistent across many tasks. And then we compared, we used ADNI, we split it. We still have a heldout, fully held out tested in ADNI, but then we used NAC data, which you can see the characteristics a little bit, as our fully external, completely untouched, data set. And our results are pretty promising in the sense that, okay, on ADNI, okay, we get decent AUCs. MCI is usually a bit of a problem, but we'll see potentially why. There's an analysis we did to look into that. But then also looking at NAC, the results, actually, the performance drops a little bit, but it's not that much. So performance seems to stay consistent. And normally, actually, precision recall curves are more important. And so we look at these ones, and we see that, from my point of view, when I looked at this one, I was like, okay, we have like 90% positive predictive value if you wanna have a recall of, let's say, 50% here, okay, roughly that one for identifying AD from others. So that already told me, you know what, maybe we should start being serious about NYU Langone already. Maybe we don't need to improve this performance from 90 to something else. And this is external validation data, so it's promising. So in a way, I kind of started to, think about already how do we engage, the radiology department, etc., and put these into real tests. Also, by the way, normally neuroimaging community is stuck on Freesurfer tool, which has been around for like 30 years or so. It's a very nice tool, but it's based on the old methodology, which is Markov random field and graphical models. It's really cool, but it's also a little bit brittle in terms of a little bit differences in terms of the intensities, devices, etc. And of course, we compare with Freesurfer-based model. And Freesurfer-based model that we build is actually already quite advanced. It's we have linear models, and we build also a random forest model, with all the volumes in the brain. And this random forest model with all the volumes is actually the better model, and we're listing here. So the performances are better, and also the drop in terms of the performance drop across cohorts is also lower if we use deep learning. That's one thing. The other thing is Freesurfer takes 11 hours to actually do per MRI, whereas deep learning model, the way we have implemented it, 7 minutes of pre-processing and then less than a tenth of a second for actually running the model. So like if we are talking about actually deploying it into our HPC system, we cannot do Freesurfer. It's just gonna wipe out the entire HPC. However, we can actually do our deep learning model. So we also, as I told you about, there is this MCI thing, which performance in general is a little bit poor, but we looked at errors of the MCI patients. We looked at patients who the model actually predicts them erroneously, with errors at AD. Okay, so that is considered an error. However, we looked at the progression, and it turns out that if the patient is not predicted as AD, they actually don't transition to AD. And then people who are predicted wrongly, like that, if they are the part of, you're counting them as error. But if we look at those patients, they actually very quickly transition to AD within a couple of years, whereas this information doesn't exist in Freesurfer based model. That doesn't give us it. So with that, as I said, we immediately started thinking about our clinical setting because we kind of have promising results already on research data. So we got data from NYU Barlow Memory Center, which is an NIH designated ADRC, like Alzheimer's Disease Research Center. They actually do a lot of interesting tests for the patients, and their care is stellar. We looked at 10 neurologists and looked at all the patients from those 10 neurologists and look at those who have MRIs. This is the distribution. We are talking about much more diverse population, like 70% white. It's just one measure compared to like ADNI data and NAC data, which were 90 and 80% white. And we looked at the performances, okay? So without training anything, without doing anything, just taking that model, which we validated on NAC, if you plug it in, there is some performance, it's not 0, it's 78 for identifying, for example, AD. However, okay, this is the model developed on research grade data, but clinical data is typically a little bit less quality, lower resolution, etc. So we simply fine-tuned the last layer of the model on some subset of the data, and the performance actually completely got lifted. So, that's very promising. And it actually is sufficient to really fine-tune it. Retraining the model doesn't give us much more. So definitely that's another interesting finding. And the challenges that we have, and the reason that is not actually this part of the study is not part of our NIH trial, is that people who typically in the clinic get ordered MRI of the brain in the elderly, they are already a very special biased subset of patients. So like it's not offered to everyone, especially lower socioeconomic status patients. So like whether or not this model will capture a lot of patients, that's a question. It's interesting, challenge for us to deal with. And also, of course, the labels are still noisy. I know that. We do have underdiagnosed and late diagnosis of MCI-AD. So it's a chicken and egg problem. How do we solve that? I think the solution is just, tackling it in cycles, improving a little bit of early detection, and then the labels will get better, etc. So that's it. I think I'm out of time. I'm gonna just wrap up that there's a lot of disparities, a lot of interesting opportunities. Both EHR and MRIs are really promising, and these tools really need to be tested in the clinical settings. So thank you.